So if you remember, we have started this unsteady heat transfer, okay? And we have a fair idea that what is Fourier's law and then how we write the heat balance. So this is basically energy balance, but then unsteady state. So it's better that we start from some problems that will give us, better feel of what is going on. And no need to mention that it is analogous to what we have done previously, the momentum transport, unsteady state momentum transport. So it is very analogous to that. Okay. Right. So there, as I told you in the last class, that all the equations format will remain identical for a given problem conditions. And the only quantity which you are going to change is the physical quantity. For example, there is something for velocity or stress. Here we will have something for heat and temperature. So basically, if you'll see, you have their velocity and stress, and you know that if you use Newtonian's law, then the stress is nothing but it's a kind of velocity gradient multiplied by this constant viscosity. Okay. So analogous to that, if you see the heat, in place of V we have temperature. Okay. And in place of this stress, we have heat flux. Okay, which is nothing but minus K dou T by dou X, or if it is 3D, then you can write this divergence of T. Okay. So that's how we can take the analogy, right? And we will mainly focus on conduction mode, because then only this unsteady state becomes, the effect of unsteady state or the transient duration is important for us. We have to capture things during that transient period. Okay. Right. So with this background, let's start a problem. This is one of the assignment problem which I've given you. Okay. So the problem statement is as follows: that we have a solid material which is occupying space from x equal to 0 to infinity. Okay. So it can be a block also, but I am only assuming that there is a 1D heat transfer. So let's say it block, but I am ignoring the transverse direction, and the heat will only flow in x direction. Okay. And so this is our x equal to 0, and this is x equals to infinity. Now I'll ask you whether this infinity makes sense or not. You all are aware that infinity always doesn't make sense. In fact, it has a practical meaning. So that we will I got disconnected or what, Sahil? Now I am audible? Yes. Okay. That's a recording is also. Fine. Thanks. Okay. Right. Okay, where is the screen? Yeah, so Aditya, any idea that when we can say this L as infinity? I am sure you have idea. So any idea? The hint is that under what time regime we can assume that L is practically infinity. Sahil, any idea?
For the early time.
Yeah, so what is that early time? That's what I want to know in terms of these various physical parameters. You are right. Yeah, L square by alpha. Your time regime should be very, very less than this time. Okay. So under those circumstances, we can say that this L is practically infinity. Okay. Thank you, Sai. So what is happening? This is the rod. Okay. And the initially its temperature is T0. In the beginning its temperature is T naught. So let's write down an initial condition. Okay. So at T equals to 0, T is T naught. Okay. For all x. And then at T, for all T greater than 0, you suddenly raise this temperature to T1 and maintain it. So this is the boundary condition basically. Here temperature is T1. So let's write down boundary condition also. So whenever you get the problem in exam, especially when this offline mode is now going on and you have to rely on yourself, write down first initial and condition, boundary condition. That will give you a feel of the problem. Many people do it later on. Do it first before solving the problem. So the boundary condition is at x equals to 0, T is equal to T1 for all T. Okay, right. And can anyone tell me what will be the boundary condition at x equals to L, which is practically infinity for early times? Okay, so we are solving it in this time regime, so there is no doubt. So provided we are solving it for this time regime, what will be the boundary condition at x tends to infinity? Shashank, any idea? T equals to, what do you think, Shashank?
Infinity.
Sorry?
T infinity.
T infinity. See, your initial temperature is what, Shashank? T naught?
Yes.
And heat is not reaching to that end because it's too early. So what will be the temperature at that point? Will it change?
No, sir.
So it will be initial temperature, T naught.
Yes.
Okay. Good. Right. So initial condition, boundary condition are same this time. Okay. Right. For all T. Because you are saying early time, so practically you are assuming heat has not reached to that point, has not traveled to that point. Okay. Right. Okay. So first of all, write down the governing equation. So let's write down the governing equation. It is very straightforward. You all are aware. So our governing equation will be we are writing the heat balance. So it's dou T by dou T is equal to, we have seen it, alpha dou square T by dou x square. Okay. 1 day heat transfer. Heat is flowing in this direction. So at any point, if you are interested in Q, heat flux, it will be minus K into temperature gradient at that point. This is the heat flux at X. Okay. Anyway, so this is our governing equation. Now we want to take the analogy from momentum balance. We can guess that the solution should be of the form of error function, because that's what happened when we solved this problem. Let me just remind you what was the problem. That this was the bottom plate, and you keep on pulling it some velocity v equal to u naught for all T. Okay, and then at early times you wanted to know the velocity profile, and the equation was, if you remember, the governing equation was dou v by dou T is equal to kinematic viscosity or momentum diffusivity dou square v by, this time it was dou y square, because momentum was transporting in this direction, fluid was flowing in this direction. Okay, right. So now if you want the solution to be in the form of error function, not only the governing equation, the boundary condition and the initial condition should also match, and that is not the case right now. We have to then modify this so that we can directly borrow the solution from this momentum balance by taking the analogy. So first let's write down the boundary condition which was there in this momentum transport problem. Okay. So the bound, if you remember, in this velocity, this boundary layer problem, so is Rakshit is there? Anyway, so the boundary condition is as follows. You see, if you consider this as y, and this is y tends to infinity, early times. So our boundary condition, if you remember, at y equal to 0, velocity is u for all t. Okay. Then at y equals to infinity, velocity is 0 for all t. This was the boundary condition. And initial condition was, because this is boundary condition, and initial condition was velocity is 0 for all y. Okay, initially fluid was at rest. So if everything, and we know that the solution of this problem is given by, remember, the solution of this problem is v by u. Okay, or you can simply say, anyone can tell me, just check your notes and tell me what was the solution of this problem for these given boundary condition at early times. Swamik, can you tell me the
Yes,
solution
sir.
of this? Yeah, just help me.
Yes, sir. Yes, sir.
Yeah, so what it was? V is equal to,
So can you please repeat the question?
yeah, so the question is as follows. You remember the problem where this bottom plate was moving with a fixed velocity, right?
Yes,
And
sir.
we wanted to know the velocity profile at early times. What was the answer?
Sir, I don't remember.
But you remember the boundary conditions?
I have to see the notes.
Okay, nice, fine. But you understand the boundary condition for this problem, right?
Yes, yes.
Okay. Just repeat it. Just explain the class. What is boundary condition for this problem? An initial condition. This will help you. Don't worry. I'm not checking you. I'm just waking you. Okay. What is the boundary condition? Go ahead.
So early times. Oh,
Yeah.
yes, sir. Yes, sir. One minute.
It is written on your screen. What is 1 minute?
Sir,
It's written on the screen which I am sharing.
said y equal to 0, v equal to u for all t.
Right. Then another boundary.
Answer for y equal to infinity, v equal to 0 for all t.
Why so? Why v is 0? Any idea? Still reason?
Sir, because it is early time.
So what early times means what? What is the consequence of early time? What is happening at early times? Say it in words. At early times.
The momentum transfer hasn't happened yet.
Very good. Wonderful. And what is the initial condition?
So the initial condition is v is 0, v equal to 0 for all y.
Right. So fluid at rest. So the solution of this, Somvik, if you don't remember, you should remember it by the way, is very famous format. U1 minus ERF of eta. And eta is what? Y divided by the square root of 4 nu t. Okay. Thanks, Somvik. So you can check your notes. This at least, see, remember the next enzyme is offline. Okay. So there is very least scope of coding. If I'll ask, then I have to solve it by pen and paper.
Okay, sir.
So you just
so if you give some problems, we have to do the analytical solution.
Maybe, yeah, because it's offline exam. Okay, so please be aware. You cannot ignore it. I'll try my best that I'll give you an alternative also that solve it numerically using, calculator and maybe 10 steps, 20 steps, something like this. But there is a chance, very good chance that you could have to solve. Of course, I will ask you the famous solution which we have covered in the class. But then you have to be aware. For all of you, I'm telling you. Okay. Don't ignore everything.
Sir,
yeah.
Sir, if you give some problem which involves like complex functions as part of the analytical solution,
Yeah.
then sir, like it will be like very lengthy and it will.
Wait, something. Wait. I am teaching this course for last 3 years. So I have enough idea that what should be like. I will give you all the functions. See, my concept is very simple for all of you. I don't want you to remember anything. If you'll apply your brain, You will get it there. You don't need to remember anything, any formula, even if you don't need to remember error function. But at least you should know the solution strategy. When error function will work, when separation of variable will work. If you are not aware of that thing, no one can help you. Okay. So just keep in mind that at least a fair idea when error function solution will work. That should, you know, that it only appears at early times. When separation of variable works, that you know that happened when you take this finite length problem. So these things, I'm not expecting too much from you. Okay, but the problem is that many people don't listen the lecture carefully, and they think that then later on they can cover. Not all of the students are smart, and you many of you won't be able to do it. The only effort which you should put it in the class, you listen it carefully, ask it. You never ask the questions. I have to, most of the times I encourage you, I motivate you. I mean, you should interrupt me. Why this? Why that? I didn't get it. I never confront those questions. I don't know what kind of class we are conducting. See, class is the best place where you can interact with me. You can learn whatever your doubt is, even if it's a very trivial doubt. That's fine. No doubt is trivial. But then I don't see that. I mean, that that kind of interaction. I generally keep interacting on fixed number of people. That is not good. You should come forward. And if you are getting it, then why I don't see that performance in the exam? Only few people are getting it. On one side, you claim that you understand, and that's why you are not asking, or you are not interacting, or you are not attending the class also. Fine, do it. But then I have no problem. I never force anyone to attend the class. But then I want to see your smartness, your performance in the exam also. So my suggestion, those who want to spare their time and want to use for other useful activities, be attentive in the class. It's only 1 hour investment. You will see generally I solve the whole problem in the class. So you don't need to do anything practically if you will listen me carefully. Participate with me. That is more than enough. You don't need to even prepare for the exam. 1 or 2 hour revision will be enough. Just go through the problems which you have solved in the class. You'll find I'll never ask anything out of syllabus. Okay. And I always give sufficient hint what I'm going to ask. If you see our this mid-sem online mode, I had given enough hint that see I can ask a problem flowing through a pipe. There I can put on a steady state. So all these hints were there. You have to listen carefully, and then you have to analyze what I can ask. I'll never ask something which I never mentioned in the class. I know it's on a steady state. It's mathematically rigorous. So I always I'm very careful while asking something. That something very difficult should not be asked. Okay. Okay, Samvik, clear, and others also. Fine. So
Yes, sir.
yeah. So this is clear, right? So early times always offer. This error function solution is a possibility. That's all you should remember, right? So if we know this, see, we are learning transport phenomena. What is the advantage if we solve all the problems separately? We should take the help using this analogy that one quantity is replaced by another quantity, otherwise everything is identical. All the equations, the phenomena is identical. Okay. So if you can get all these boundary condition, initial condition for this problem, heat transfer problem, then we can directly borrow this solution. We'll just replace V by something else. Okay. Now, who will help me? See, right now the boundary condition doesn't match. Let's say if I take the boundary condition, it does not match with the boundary condition here. It should be 0 at one boundary at x equal to 0, and sorry, it should be v equal to u, means if you non-dimensionalize it, v equal to 1. In non-dimensionalized form, v equal to 1. Okay. So what we should do in order to have this boundary condition, basically this is nothing but in non-dimensionalized form, v equals to v by u equals to 1. Okay. And here v by u equals to 0. So what we can do? So let's define a new variable, theta. Okay. And here you want that value, okay, or if you put, let's say v equal to v equal to u, that is also fine. We can borrow the solution. So you want t equal to t1. Okay, so just wait. What we can do is, in fact, think about the another boundary here. At infinity, you want to make it 0. So what you can do, if you want to make it 0, then let's define theta as t minus t naught. What is the advantage? Can anyone tell me, if we take theta as t minus t naught, then what will be the this boundary condition? At x tends to infinity, what we will get? What will be theta?
0.
0. Okay, so what, right? And then at x equal to 0, theta will be anyone? T1 minus T naught. Okay. So I am not non-dimensionalizing it. You can, there is no problem. If you want, we can non-dimensionalize it also. That's not a problem. Okay. But T1 minus T naught is also fine. Okay. So my new quantity is theta. Okay, let's check initial condition. Boundary condition is matching. This is in place of u. This is my u. T1 minus T naught. Some number. Okay. Let's try to match this one. So if we'll see, what will be the value of this initial condition? Anyone? Theta equals to
0.
0. T naught minus T naught 0. So you just need to put this various value at the place of T1. Okay. So now if I'll write it here, again, just to remove, avoid any confusion, my governing equation is dou square T by dou x square is dou T by dou T. Now what I am saying, I'll put this minus T naught here also, which is fine because it's a differential. So differential is 0, and here also T minus T naught. Okay, and then I say this T minus T naught is theta. Then I will have dou theta by dou T is equal to, sorry, alpha is here, alpha dou square theta by dou x square. And now if you write the boundary condition, theta, so if you take x equal to 0, theta has some value which is T1 minus T naught for all t, of course, because it's boundary condition. At x equals to, x tends to infinity, theta is 0 for all t. An initial condition at t equals to 0, theta is 0 for all x. Okay. So now it is matching. The only thing is that we have this number in the place of u. Okay. And what is our eta, by the way? Anyway, we don't need eta. We are directly going to write this solution. So let's use this solution because now it is matching. You see, at infinity, the physical quantity value is 0. Initial condition, the physical quantity value is 0. And at y equal to 0, the physical quantity value is some value. So we are replacing v with theta. Simple. Okay. So the solution of this is directly taking the analogy from, that's why we are learning this transport phenomena, taking the analogy from that velocity problem, that momentum transport problem. Theta is equal to, can anyone tell me, in the place of u, what we will write? Now this you should tell. In place of u, anyone? See, this u is the value of that physical quantity at x equal to, here at y equal to 0. What is the value of that physical quantity at x equal to 0 in this problem? What is your value of theta?
T1.
No, T1 minus T naught. You see, you're right. Your governing equation is in terms of theta, isn't it? So what is the value of theta at that place? Is it clear? Whoever said T1?
Yes, sir.
It should be T1 minus T naught. Zombie, is it clear? Why it is T1 minus T naught?
Yes, sir.
Yeah, because theta is the quantity which we have defined is this, and the value of this quantity at x equal to 0. So this is nothing but T1 minus T naught. Okay. Then what is this? 1 minus ERF of x divided by square root of. Now this I'll expect from Somvi. Sorry, today I'm, but tell me here what we should write. You can see here and tell me. This is 4 nu t, square root 4 nu t. What it should be here, Somvi? It's an easy question. Just see the equation carefully and tell me what it will be. In place of y, we have x because we have taken x as the flow of heat direction. What it will be? Yeah, Samvik, what it will be?
Yes, sir.
Yeah, in the denominator, square root of?
Sir, can you show the previous page? I got disconnected for it.
4 nu t.
Yeah.
See, 4 nu t. This is the penetration, that momentum diffusion length scale, square root of 4 nu t.
Yeah.
So what it
So,
will be? Yeah.
for alpha theta.
Very. Theta. Why theta, Samvik?
No.
It's time.
Yeah.
So why theta then? T, simple T. Okay. Theta is for temperature, not for. Are you getting this? Okay. Is it clear? Anyway. So theta is this. Now, if you want to check whether it's correct or not, it's very okay. Now you can write theta in terms of our actual. So what was our theta actually? Theta is nothing but t minus t naught. Okay, you see. So t naught we can send that side. So t naught plus t1 minus t naught 1 minus ERF of x by square root of 4 alpha t. Okay. That's it. If you want to check whether it's correct or not, let's check the boundary condition, initial condition. Let's say someone wants to check boundary condition. So one boundary is x equal to 0. If you put x equal to 0 here, can anyone tell me what is the value of ERF 0? Just check on the just Google it, error function calculator, and tell me what is ERF of 0. Because when you put 0, this will be 0, ERF 0. Anyone? What is error function of 0? Value of ERF 0? Yeah, anyone. I'm going to name
0.
ERF of 0 is 0. Okay. If you say so, let's see whether correct or not. So T1 minus T naught, and as you said 0, so 1 minus 0 is 1. Fine, good. So you see at x equal to 0, you are getting T equal to T1. Wonderful. And the same person, thanks a lot. Now you help me here also. Now we are going to put infinity. Just check ERF of infinity. Put any big number in the calculator, or you can directly type ERF infinity. So t equals to anyone. What is ERF infinity plus T1 minus T naught 1 minus, yes, what is ERF of infinity?
1.
1. Very good. So 1 minus 1 0. This is gone. So at x equal to infinity, t equal to T naught. So both boundary conditions are matching. Let's see the initial condition matching or not. So for initial condition, what we'll put? We cannot put t equal to 0. So we'll put t tends to 0. So when you put t tends to 0, this becomes ERF of infinity, and again you will get t equals to T naught. That's it. Okay. In fact, I will not mind if in the exam you directly write this solution. I will not mind it. That's fine. It's offline exam. There is no chance of copying. So I don't expect detailed solution from you. If you directly write, this is the solution for this given boundary condition, it's fine. You can save your time. Okay. Great. Let's move ahead. So, so this was the solution. Now what else has been asked if you'll see the assignment? Find the time dependent temperature profile. So you see this is the time dependent temperature profile. If you'll see carefully, you can plot it also using MATLAB or any other plotting software. So this is what, let's see, T naught, T1 minus T naught plus T1 minus T naught 1 minus ERF of x by 4 alpha t. So if you want to plot it, here you will have temperature, and here you will have x, okay, and then you will plot it for different time. So let's say at some time t equal to t1. So then this number is fixed. Then you have t only as a function of x. So you will get some graph, okay. So of course this temperature will start from t1, and then it will decrease, and of course it will never go to 0. It will go to the initial temperature, because you are assuming that still significant part of that rod is at initial temperature. The effect of heat which you are providing at one end has not reached to up to the end. So this is, let's say, at some time t1. Then at some time t1, then you want to know the temperature as a function of at equal to t2. This will be like this. Again, this will also go here, okay. Right, and so on. So gradually heat will penetrate more and more. So if you see, this is the increasing time, okay. What else I can tell you? Yeah, so the way you have seen that we have this momentum diffusion length scale 4 nu t, that if you know the time, you have a rough idea of up to what length momentum has diffused. Similarly, here we have thermal diffusion length scale, okay. Thermal diffusion length scale, and this is 4 alpha t. So for a given property of a material which is alpha, at a given time you can tell someone that up to what length heat has penetrated or the effect of heat has gone, okay. Rough calculation, because that's what we looking forward as an engineer. Sometimes we are not interested in the precise answer, a rough estimate, okay. Right, what else? If you see the assignment, other thing which has been asked, so that the flux at x equal to 0 value, that is easy, that you can calculate, because if you know t, you know q also. If you know t as a function of x, it is nothing but minus k dot t by dx. So you just need to differentiate and you can do it. And then prove that the penetration depth is given by this, so that you can see I have defined how we define a penetration depth. So that is easy. That is just mathematical treatment. So this is done, error function. Now let's move to another problem. Anyone has any confusion? Let's wait for 2 minutes. Anyone has any doubt? Feel free. If something you didn't get or anything. Meanwhile, I am just going to another problem. Take your time. If you have any doubt, we can do. Okay. No. Then we will go to another problem, which is given in your, which I've already. So let me just open that, which I've uploaded here. Files. So this is similar kind of problem, but there is a small twist here. So let me discuss it with you. So here, rather than fixing the temperature of the one end, this time you are fixing the flux on the one end. So let's see this problem. Yeah. So let's first read the problem, because that is the most important part, and then I'll tell you how to solve it. It's already solved, so it will not take much time. So as you can see that, yeah, so what is, suppose you are visiting Iceland in winter season and you have planned for skating on one sunny day. The skating field is uniformly covered with thick layer of ice, okay, above the ground. It has been strongly suggested to you not to do skating as soon as the top surface of ice starts melting. Hence, in order to avoid any accident, you plan to calculate the time up to which skating will be safer after sunrise. So a schematic, so you see, this is a real life problem, okay. This I have given sometimes in the exam, okay. So you can expect similar kind of problem, maybe 2 years back or 1 year back, I don't remember. Right. So what is happening here? So this is a real life problem. Now we are going to model it. Okay. So first I have described the phenomena, real life phenomena. Now see how, as an engineer, how we can model it. So schematic has shown below for clarity. Okay. So now I'm just modeling it. So you see, this is the ice, thick ice sheet which I'm saying. Huh? So let's say thickness is 2 meter. Okay. Initial temperature of ice is given, minus 10 degrees Celsius. Density is given. Okay. The thermal conductivity, all the physical properties are given. And sunrise happens at 8 a.m. Melting point of ice is 0 degrees Celsius. So after the sunrise, the top surface ice gets constant heat flux. So what is happening? As soon as sun rises, your top surface starts getting heat at this constant rate, this constant flux, 350 watt per meter square. So the flux falling on the top surface is constant, not the temperature. So initially, before the sunrise, this whole ice block, the thick layer of ice block, whose thickness is fixed, I am saying 2 meter, was at minus 10 degrees Celsius. As soon as sun will rise at 8 a.m., heat will start falling at constant rate, constant flux rate, or constant flux will fall on the top surface, and hence the temperature of whole ice block will start increasing. So can you guess which layer will be at the highest temperature with time? Like if I draw a temperature profile from top to bottom, at which location temperature will be always higher as respect to the other location? Anyone? Which location?
Y equal to
Sorry,
y equal to 0.
a bit louder.
Y equal to
Y
0.
equal to 0.
Y equal to 0, the top layer. Like if I don't define y, so y equal to 0, not y equal to 2. Someone said y equal to 2. No, the top layer. Okay, because the top layer is the first layer where the sun rays will hit. So this layer will get first heat, so its temperature will be higher than other layers. Of course, gradually heat will penetrate into the into this ice cube, and then gradually the temperature of the whole part will start increasing. Okay. So what is happening? The temperature of this whole ice block is increasing, and for a given instant, the temperature of the top point will be highest and the bottom part will be lowest. Okay. And hence the temperature will rise from minus 10, the top layer, which was also initially at minus 10, that will start rising. And when it will reach to 0 degree, ice will start melt and you have to stop skating. So, yes. Someone is saying something. Oh, nothing. Anyway. Yeah. So, basically what you need to find out, can anyone tell me what we need to find out here? Which time? The time after which the top layer temperature will become equal to what?
0 degree.
0 degree. Wonderful. So see the top layer, if I describe this problem before solving, the top layer is initially at minus 10 degree. Now this heat is falling. So of course the temperature of whole block will start increasing, but this layer will first achieve the higher and higher temperature. So its temperature will increase with time, and after certain time, okay, let's say some time, its temperature will be 0 degree, and then this top layer will start melting. You have to stop the skating. So that's what I have asked, that what is that time? After what time? 8:30, 8:40, 9:30, after what time you have to stop the skating, because it is not safer. Okay, now let's see how we are going to solve this problem. So if you will see here, the boundary condition is constant flux. So if you go from this temperature approach, it may not work, because the boundary condition is not given in the form of temperature. Another thing, in case I forget some assumption, you mention it, but I have here mentioned it. Consider only 1 day heat transfer. I am making the problem simpler, because as an engineer, I just want a rough estimate. So I will not take a very rigorous problem. I will say, okay, let's assume only heat is traveling in the downward direction. So 1 day heat transfer in y direction. Okay, all the identities are given anyway, so fine. Right. Alpha you can calculate because K by rho Cp is alpha and all the values are given. You see K, rho, Cp. Okay, so thermal diffusivity you can calculate. So everything is given. Now let's write down the governing equation. So governing equation is going to be same. So you see this is our y equal to 0, just to mention, and heat is flowing only in this direction. So it's simply a 1D problem. We know governing equation is not going to change. Fundamentally it's same, heat balance. So this is my governing equation, no change. It should be y by the way. Okay, but anyway, so let's make this as x so that, or you can replace this x by y. So this is our governing equation, but the boundary condition is not given in terms of this temperature. So I have to convert this governing equation itself to the another physical quantity, which is Q, heat flux. We know Q is minus K rho T by dou X. Fourier's law. Someone asked me in the last class. He said he knows the law, but he doesn't know the name of the law. Okay, that's fine. Okay, so this is now what you are going to do. You are going to, with the help of this, let's say formula A, you are going to convert this our governing equation from T to variable Q. So what I have done simply, it's very simple. You see what I have done. I have taken this dou by dou X both sides. Okay, on the in this equation. And then I have used the exchange of variables. So T went outside and X came inside. Similarly here also. Okay. In fact, here I have done nothing. This is as it is, nothing. Now this term I can write like this, minus K dou T by dou X, dou by dou X. Okay. Let me show you again carefully. This term, okay, I am writing as dou of dou X minus K dou T by dou X. And here also we have minus K dou T by dou X. And we know minus K dou T by dou X is nothing but Q. So this will be replaced by Q. And here we will have Q. So this will be dou Q by dou X. So at the end, what we will get from here, you will get what? Dou Q by dou T, because this term is Q. Okay. Heat flux at a given location is equal to alpha dou by dou X. And we have just seen this term came out to be dou Q by dou X. And then there is one more dou by dou X. So this will be double derivative. And at the end, this is my governing equation. So you see what happened? The only thing is that T got replaced by Q, but the mathematical format is same, right? Okay. So this is fine. So from here we came to here using this definition of heat flux or Fourier's law, you can say. We are here now. Now we should worry about the boundary condition. Okay. And if it matches with, now it has been asked what at if you have if you are listening the discussion, we are interested in that after what time the top layer temperature will reach to 0 degree. So you see we are still confined to the top layer. We are not worried about the rest of the domain. So we can safely say that if I solve my problem in early domain, early times, I'll surely get the answer, because early times means what? Only the the top layer here got affected. Still the rest of the part have not received any heat, because that's what I'm looking for, that after what time in the vicinity of top layer it will be 0 degree, or the top layer precisely will be at 0 degree. So I can safely say, since I'm only worried about the temperature rise up to what time it will go to 0 degree, I can say safely say early times, but we'll verify it. How will verify it? You can always calculate L square by alpha. Okay. And let's say L square by alpha is coming some value. We can calculate it. Can anyone tell me what is the value of L square by alpha in this problem? First tell me alpha quickly. Let me see who is there who can help me. Because if I ask someone who is not in the class, physically in the class, mentally somewhere else, it will be a wastage of time. So maybe Adrija can help me today. Adrija, if you are there, you can hear me. Just calculate alpha. First you respond and then answer.
Yes, sir. Yes, sir.
Yeah, yeah. But so let me show you the value. Huh? Just a moment. Just a moment. I have to. I think the problem is here. No? Oh, it was there itself. I have to again go here, files, and this one. Yeah, right. Yeah. Now you can see these things. The value. Can you tell me alpha now? I think I have downloaded it. It's here. Now you can tell me alpha. Yes, Adrija. So in fact, not alpha. Tell me the value of this L square by alpha. Just to get a time estimate. Okay. So first tell me what is alpha. Alpha is K by rho Cp. So all the values are given. Yeah. So K is 2.3. All are SI units, so no issue. K is 2.3 and rho is 918.9 and Cp is 2000. Just tell me what is alpha.
So 1.25 minus 6.
Right. So that's what. Remember, these values should be of the order of 10 per minus 5, 10 per minus 6. If not, then you are making some mistake. If you are getting 10,000, certainly you are doing some mistake because alpha cannot be. It's like diffusivity. It's always in the order of 10 per minus 6, 10 per minus 5 meters square per second or less than that. Okay. So then, Adrija, just go ahead and calculate this time scale, L square by alpha. So our L is 2 meter. So 2 meters. So we can say 4 divided by 1.25 into 10 to the power 6 roughly. So forget about this 4 by 1.25. Just say 10 to the power 6. So 10 to the power 6 seconds. Just convert it into hours. 10 to the power 6 seconds. Hours. So we are ignoring this number. We just a prefactor. So seconds. How many hours? Anyone?
277.
So 77, 78, something like this, right?
277.
278. Right.
Yes, sir. 277.
So 278 hours, right? If I can, so this is the time scale after which you can expect that heat will actually hit the bottom layer. Okay. Now, if you solve this problem taking this error function in consideration, and let's say the time which you calculate comes out to be 2 hours, that after 2 hours top layer will start melting. Can I claim that error function solution is right or wrong? What do you think, Adrija?
Yes,
What is your
yes.
comment? Yes, because 278 hours is so 2 hours is very small as compared to 278 hours. So we can safely say it. So that we will check. At least from this calculation we know that at least it will take 200 hours, minimum 200 hours to reach that effect to the bottom point. तब तक में तो रात हो जाएगा फिर से. Anyway, so we are saying it's a early time. Okay. And if we are saying it's early time, and if we say solution is in the form of error function, the boundary condition should be a particular boundary condition, which we have seen just in velocity problem, in temperature problem. Here it should be in the form of Q. So let's write down boundary condition quickly, and then you can leave. I hope you are enjoying. I'm trying my best to motivate you, encourage you. So x equal to 0. What is boundary condition? Anyone? I will not take the name. So we are now, see, this is our governing equation in form of Q. So write down boundary condition in form of Q. What is Q at x equal to 0? This say x. Anyone?
350.
Q naught, it is given. 350 watt per meter square. Some value, just take Q naught. That value we'll put later on. And can we say other boundary, since we are saying it's error function solution, early times, of course, I will assume that other boundary is infinity. Okay. And what is the Q there? So now we'll say we don't know. Fine. We don't know, but we know Q is minus K dot T by dou X. And since you are saying heat has not penetrated deeply, so probably in this region, temperature is still minus 10 degree everywhere. So temperature is constant in this region. T is minus 10 degree everywhere. So what will be the gradient if temperature is constant along the x in the bottom region? What will be its gradient? Anyone? If T is constant with respect to x, yes?
0.
0. Okay. So another boundary condition is 0. Okay. So now I'm removing this minus k dot T by dot x. Q naught 0. So boundary condition is done. Let's write down initial condition. So again, what is the value of Q initially at T equal to 0 for all y? So again, take the help of minus k dot T by dot x. Initially, temperature is what at all places? Anyone? Minus 10. So what is the value of gradient in the beginning if temperature is uniform everywhere?
0.
0.
0.
Right?
0.
Right. Thanks. So now you see this problem completely matches with what we have done in the velocity problem. The only difference is that V is replaced by Q and the initial condition, one boundary condition U replaced by Q naught and another boundary condition is 0, like we have 0 here, there also. At one boundary it was U and another boundary it was 0 and initial condition was also 0. Here also we have Q is 0. It means there is no harm. I mean, we can directly borrow the solution. We will not solve it. The only thing is it is not in the form of V. It is not in the form of temperature or theta. It is in the form of Q. And my answer is Q equal to simply Q naught 1 minus error function of x divided by square root of 4. Not new. It's alpha hit alpha t. Okay. But we are somewhere in the midway. In the next class, now, so this is, we got heat flux answer. Now we'll again go back to this definition of Q, which is minus k dot T by dou x, and then we have to integrate it, and then we can find out that by solving the differential equation, we can find out the temperature profile. And once you know the temperature profile as a function of x and t, you can then you put x equal to 0. If you put x equal to 0, you will get the temperature profile of the top layer as a function of time. That how top layer temperature will vary with time because you are fixing the location, and then you can calculate that where after what time temperature will reach from minus 10 to 0. That time will be your answer. So with you can try this. It's solved completely in the, I think, or I'll sell the solution, and again we will meet in the next class and we'll work on this problem. Okay, we'll complete it. And then 2 more problems are remaining in the heat transfer, which we'll do quickly. And I'm checking your copies. Almost more than 60% copies are done. I'll return your copies soon. Thank you. Thanks for your extra time. And enjoy the Spring Fest who are here in the campus. Thank you.
Thank you, sir.
If any doubt, I'm here. Thanks. Thank you. I'm here.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks. No problem. You can join your other class.